All right. Good afternoon, everyone. Hope you all are having a great time at the summit here in Lisbon. I certainly have enjoyed all of the talks and also connecting with friends and former colleagues after a while. So it's really good to be here. Here at Intel, we are truly embracing a systems-first approach towards building large-scale AI infrastructure. And today, I'm going to talk about that approach and our thinking around building scalable systems for AI at the data center scale. So besides talking about general principles and approaches towards building these systems, I will also dig deep a little bit specifically into what we are doing with our recently launched Gaudi 3 generation of data center accelerator products for AI that was announced just a couple of weeks ago, so just fresh off the press. So with that, let's jump right in. So why does a systems-first approach really matter? Here are a few reasons. I'm sure there are plenty more, but just as a bird's eye view, first and foremost, the data center is fast becoming the unit of compute when it comes to AI. The optimization point that both software and hardware professionals are optimizing for is no longer an individual ingredient or an accelerator, but it's the entire data center. So the conversation is rapidly shifting away from optimizing at the teraflops per watt level at an accelerator to optimizing for the exaflops or petaflops per megawatt scale at the data center. Similarly, all of the TCO optimizations are no longer just limited to focusing on the individual accelerator, but are now spanning to the entire data center. Secondly, this should not be news to any one of you, but there has been a near exponential growth in the adoption of large-scale AI infrastructure. And the reasons for that are twofold. One is obviously to support the ever-growing growth in or ever-growing size of models that are being trained and deployed for AI. But secondly, there is also a near exponential growth in the developer count that has been focusing on AI development over the past 5 to 10 years. I mean, ever since 2012, when AlexNet revolutionized the field of computer vision, and then in 2017 or 18, when BERT came along and just changed the landscape entirely on language modeling, the developer count has actually increased quite substantially, which is why the need for large-scale AI infrastructure. And finally, we cannot accomplish a true systems-based approach until we look at the stack end-to-end. So a vertically integrated full-stack AI platform is really the only way to take on a systems-based approach to meet the needs, ever-growing needs of developers. When I say developers, it's both the software, the AI, machine learning experts, and also the infrastructure software developer persona. Which is a good segue into this slide, which talks about what exactly does it mean to take a systems-based approach. Starting with ease of use and developer productivity, I talked about the two developer personas. We, as infrastructure providers, need to ensure that whatever is put out there in the data center is easy to use for all kinds of developers. Second is the aspect of multi-tenancy and all of the security and isolation guarantees that need to come along with offering multi-tenant solutions. This is especially true in the case of the large public cloud providers, where they support at any given time hundreds or thousands of customers on just a single cluster, not just for mainstream infrastructure, but also for AI infrastructure going forward. A corollary of that is the notion of managing the infrastructure efficiently through intelligent orchestration frameworks and also job schedulers. Today, the world is all revolving around Kubernetes-based infrastructure for this. but there may be other frameworks and frameworks at a slightly higher level of abstraction that may be coming along. So infrastructure providers need to be cognizant of that, and a systems level approach needs to comprehend that aspect as well. Next is lifecycle management for the end-to-end lifecycle management for the cluster itself, meaning starting with the initial deployment of the cluster all the way to actually allocating capacity to individual customers and then end of lifing it. All of that needs to happen in a seamless, automated way, which also needs to be comprehended from day one when we start thinking about these designs, these clusters. And comes along with that is the control plane, because the control plane, besides the data plane, which is the compute, is something that orchestrates all of this. So we talk less about the control plane, but that's very important as well. Obviously, workloads need to scale because there's no point in building large-scale systems without ensuring that scalability frameworks that allow workloads to run on that large-scale infrastructure are taken into account as well. And finally, but no less important, is the hardware itself. Us, part of the OCP community, especially should align with this notion of a standards-based hardware approach towards system design, because there is only certain amount of room for diversity in the infrastructure. But if we want to make AI infrastructure truly ubiquitous, I think a standards-based approach is the only way to go about it. So with that general framing of the approach, let me jump into a few specifics about our Gaudi 3 accelerator product that was launched a couple of weeks ago. The Gaudi family of products is a truly AI-optimized accelerator family, and does not suffer from the incumbencies of traditional GPUs, which need to support certain graphics functionalities as well. So purpose-built for AI, with 64 tensor processor cores and 8 matrix multiply engines, which are the heart of the compute element in the accelerator. Besides compute, memory, as you all can appreciate, is extremely important. So 2 tiers of memory, HBM, large capacity, 128 gigabytes, tons of bandwidth, 3.7 terabytes per second. But equally important is the on-die SRAM, which offers a caching layer for software to for effective reuse of activations in the AI modeling context, which offers significantly higher bandwidth even compared to HBM. And finally, networking, which forms the third pillar of the accelerator complex. 24 integrated NICs, each of which are capable of serving traffic at 200 gigabit per second, leveraging 100 gigabit SerDes, which packs in a lot of punch and creates a very efficient and well-balanced system, and PCIe Gen 5 for the host interface. This allows us to take a very modular approach towards building these clusters, starting all the way from a single node, which is the basic scale unit, to something like a 64-node cluster, which becomes a scalable unit for a data center scale design, and then expanding that to something like a 4,000 accelerator complex or even an 8,000 accelerator complex. I will not go into the speeds and feeds in detail. You can look at it offline. But the idea here is modularity. So how we go about accomplishing this modularity is to ensure that it is baked into the design from the very fundamental or the foundational layer of the infrastructure, which is, in this case, a node comprising of 8 of these accelerators on a OCP compliant UBB baseboard. They have a all-to-all mesh of fully connected interconnects between all of the 8 Gaudis that offer an incredible amount of bandwidth for scale-up, given that the tensor model parallel domain for model parallelism typically extends to 8 GPUs in today's world. And then there are 3 links out of those 24 that I talked about earlier that are pushed out to OSFP connectors in the server that allow for scale-out, which brings me to this, which is a node-level architecture showing the OSFPs, which can then be leveraged to build out what we are calling here a subcluster that comprises of 128 accelerators. In this case, this becomes the scalable unit. As you can see, it is quite flexible. There is a leaf switch tier. We typically resort to, as you may know, a full-fat tree clause type network, non-blocking network for AI use cases that has two layers of switching. So this is the leaf layer. And then building on top of this, we can go about building even larger clusters with a two-tier switch hierarchy. In this case, showcased as a 4,000 Gaudi 3 cluster, fully non-blocking fat tree, as I said earlier, and allows us to offer customers the ability to train the largest of the models. We are talking about trillion parameter range here on this kind of infrastructure. Now, I would be remiss if I did not talk about our sustainability efforts on Gaudi, especially in the context of this regional summit at OCP. Besides the traditional air-cooled version, we also support two flavors of liquid cooling, single-phase liquid-cooled designs and two-phase liquid-cooled designs based on cold plates. The uniqueness of this design is that a common cold plate serves both cooling solutions, and we are on our way to launch the air-cooled product first, and then quickly following that, we'll be launching the liquid-cooled products as well. So very committed to the sustainability effort here. But speaking of sustainability, we obviously are not just confined to the Gaudi family of products here. At Intel, as you all know, we have a huge CPU business as well, focusing on Xeon. So this slide tries to cover our overall cooling infrastructure solutions for both the Gaudi family and also for our Xeon family. And more notably, this includes both liquid-cooled solutions and also immersion cooling, which is fast emerging as a far more efficient cooling subsystem. It will take some time to gain traction in terms of mainstream deployments, but we need to pay attention to it from the get-go because the numbers are staggering. Like we are talking about 30% of reduction in power consumption just by virtue of leveraging immersion cooling. You saw the other talks in sessions earlier today where with immersion, people are talking about PUEs of close to 1. That probably is the only path for us to get there. And like I said, our Xeon family of products also supports a single-phase, two-phase, and actually goes on to support immersion cooling right now with the third, fourth, and fifth generation of Xeon, and the recently announced Xeon 6 family, which will all support immersion cooling. With that, this is my last slide. So in conclusion, I would just like to say that we are super excited to continue our journey towards a systems-based approach for AI infrastructure. The call to action is here for you all to come participate in that journey with us. We are looking forward to collaborations across the industry to create an open ecosystem for AI systems as opposed to a closed source proprietary set of technologies. With that, I thank you for listening in, and I'm happy to take any questions. Thank you. Okay, yeah.
What about my name is Saurabh from Google.
There's a mic here. Never mind, just speak up. I think we're going to spend more time trying to transfer the mic. Go ahead.
My question goes for what about Gaudi support on immersion? Why
We are not ruling out support for Gaudi 3 with immersion. It is just going to be based on customer asks because when it comes to deployments for something like a Gaudi 3 scale infrastructure, we need to work closely with a lead customer to enable something like immersion cooling. We are definitely not ruling out. It's just not currently in our POR plans. Sure. Any other questions? If not, thank you again, and I appreciate your participation.